continue the discussion about computing transition probabilities. One step transition probabilities I showed you, and we had just started talking about two step transition probabilities. So, just consider a case. In the last lecture I considered the case x 2 equal to 1, x naught equal to 1. Now, let us look at x 2 equal to 2 and x naught equal to 1. So, in that case you see what are the possible routes of transitioning from the initial state of 1 to the state 2 in 2 steps. So, want to look at it, and of course, the 3 possible paths would be, see, at state 0. So, this is time period 0, time period 1, time period 2, and these give you the states. So, therefore, at time 0 the system is in state 1, it transitions to state 1, that is a possibility, because in one step you may transition to 1, 2 or 3, and then you have to come back to state 2. So, therefore, one possible route would be from 1 to 1 and then 1 to 2, right. So, in one step transition in one period you go from 1 to 1 and then from 1 to 2. Similarly, you could go from 1 to 2, that means you transition to, so this was our production and this is HR. So, from production to HR and then HR to again HR, right, you can continue here, or the third route would be from 1 to 3, that means from production to sales and then sales to HR. So, these are the 3 routes, and that I have written down the 3 routes in this way. Okay. These are the 3 possible ways, no other route is possible of going from 1 to 2 in 2 steps, right. Okay. Now, we need to compute the probabilities of traversing these paths, because we want to compute 2 step transition probabilities. Now, look at the first path. So, the first path I know the probability of transitioning from 1 to 1, when I am initially in state 1 and I am now transforming or transitioning to state 1 in the next time period, then it is P 1 1, I know that. Now, look at this part of the leg. So, there are 2 parts of the journey from 1 to 2, for example. So, this is this. So, first leg I know, we already know these are the one step transition probabilities. Now, we use the Markovian property, because you see the probability that you want to compute is of going from 1 to 2 in, that means you are actually looking for probability x 1 to 1, you are in 1 at time period 1 and you want to transition to 2 time period 2, right. So, then you see this is independent of the first leg. Why? Because you see this is the Markovian property says that from here to here the transitioning probability is independent of where I was at time 0, the initial state. So, it is independent of the value of x 0, right, and therefore, I can write the probability of traversing this path as product of the first leg into the probability of the second leg. So, this is the idea, and this is where I am using, and otherwise I would not be able to write these transition probabilities, 2 step transition probabilities, if I did not have the advantage of the Markovian property. Okay. So, it is clear that, because as remember I said that the past history is not important for computing, is not required for computing the transition probabilities. So, here it is where you are currently and where you want to transition. So, this is the only thing that we need to compute the probability. I do not need to know where, what was the value of x naught, right, and so therefore, the 2 are independent, and since by our stationarity. So, the stationarity property, I should say that stationarity property gives us, says that probability x 1 equal to 1 and transitioning to x 2 equal to 2, that means the conditional probability of being in 1 and then transitioning to 2, this is same as probability x naught equal to 1 transitioning to x 1 equal to 2, right. So, remember, because we said that stationarity says that probability x n plus 1 equal to j given x n equal to I is the same as probability x 1 equal to j given x naught equal to I, right. So, the stationarity property says that these one step transition probabilities remain the same no matter in which time period you are, and therefore, this transition probability of going from 1 to 2 was the same as probability x 0 equal to 1. So, going from here to 2 in the initial stage. Okay. So, therefore, we are able to write down the probability of traversing these paths, and so I have written them down here for all the 3 paths. So, this is for the first path, this is for the second one, because you are going from 1 to 2 and then 2 to 2. Okay, why have I written it as 1 P1? Oh, okay. This was 1 to 2, and here I am using the fact that you are going from yeah, what is this path, x2 equal to 2. So, what is the path I have written here, x naught equal to 1. So, 1 1 and 1 2, 1 1 and 1 2. So, this is the path, right, and then you have 1 2 and 2 2. So, that should be so this is that one, and this is this one, and this is the third one, 1 2 3 and then 3 to 2. Okay. So, this is 1 1 and 1 2, and this is 1 2 and 2 2. So, that is the one which I have written here, and then this is the one corresponding to this, and then this is 1 to 3 and 3 to 2. Okay. P11, see, okay, I do not know why am I writing this as x naught is 1, and then you are going to what is this path? This will be 1 3, and then this will be 3 2. Oh, okay, sorry. All these 3, yeah, I am sorry. These 3 paths together give you this probability, right, of x naught equal to 1 and x 2 equal to 2. Yes, this is, so these are the 3 possible ways of going from 1 to 2 in 2 steps, right, 2 step transition. So, all these 3 add up to this, yeah, I am sorry, this is the one, right, okay, P11, P12, and then P12, P22. So, this is P11, 1 2, then this is 1 2, 2 2, which is this path, and then it is 1 3 and 3 2. So, 1 3 and 3 2. So, these are the things. So, now similarly, when you want to, when your x 0 is 1 and then x 2 is 1, okay, that means in 2 steps you want to transition from 1 to 1. So, again you will have 3 possible such paths, right. Maybe I will just again repeat the whole thing, so that there is no confusion. So, for example, you can go from 1 to 1 and then 1 2. So, this is here, see the path corresponding to this will be this, right. So, maybe I make it this thing, yeah, just to, and then what is the possible way you can go from here. So, 1 to 2 and then 2 to 1. So, 1 to 2, yes, and then 2 to 1. So, this is the one, right, and then the third path would be when you want 1 to 3 and then 3 to 1, right, 1 to 3. So, you would go from 1 to 3 and then 3 to 1. So, this will be 3 paths, and then for each path you write down the probability. So, this corresponds to the 3 exclusive paths through which you can go from 1 to 1 in 2 steps, okay, and similarly this will be 3. So, now you have computed all the 2 step transition probabilities for when x naught is 1, right, and then in 2 steps you can be in 1, 2 or 3. And so, similarly you will have 6 more such transition probabilities when x naught is 2, and then you want to transition to 1 or 2 or 3 in 2 steps, starting from state 2 at time 0, okay. And then finally, it will be x naught equal to 3. So, x naught is equal to 3. So, because you do not know, you could be in any of the 3 states at the beginning of the process, and so x 2 is equal to 1, you are transitioning to 1 from 3 in 2 steps, from 3 to 2 in 2 steps, and from 3 to 3 in 2 steps, right. So, let P 2 denote the matrix of 2 step transition probabilities, just as P, we are not writing P 1, it is understood P 1 we is said is P. So, this is a transition matrix of 1 step transition probabilities. Now, let P 2 denote the matrix of 2 step transition probabilities, then we will just quickly notice that P 2 is actually P square, because yeah, here you have written the components of this. Let me just write down, say for example, if you want to write, so P 2 this here will be, the first one will be P 1 1 2 you want to look at, right, and so that will be going from, so P1 2 P21 plus P13, oh okay, first of all it will be 1 1 1 1, then it will be 1 2 P21 plus P13 P31. So, this will be your first element, right. These are the 3 paths which I had drawn in the last lecture. Okay. So, then you see this is multiplying P11, P12, P13, the first row of P, and with P11, P21, P31. Yes. So, if you multiply the first row of P with the first column of P, you get the entry P112, right. And now you can also verify this. For example, this is the first row P11, P12, P13, you are multiplying with the second column P12, P22, P32, right. So, to get the entry 1 2 in 1 2 in, that means here if you want to get the entry 1 2, then you are multiplying the first row of P with the second column of P, and therefore, you can just verify yourself quickly that P 2, the second step transition matrix, is nothing but the product of P and P. So, that makes life very easy, and we will show that this is valid for all values of, for higher powers of P also. That means, if you want to look at, yeah. So, let me just show you systematically that we are really on the path of getting a very interesting and very useful result, because to be able to compute these transition probabilities, any step transition probabilities, by raising the power of P is a very convenient way of getting the transition probabilities, right. So, if you want to know that what is the probability that you will be in 10 steps, you will be from I to j, starting in state I, you will be in state j, then the 10th the ijth entry of P10 will give you the that probability, and so on. So, we will see that. Yeah. So, basically what we have done, we have shown is that your 2 step transition probabilities can be expressed in terms of 1 step transition probabilities, right, because we are just multiplying the 1 step transition matrix with itself, and we are computing the 2 step transition probabilities, right. Okay. Now, the same way we can do it for any power, and here again I just want to spend time. It may look like a little repetition, but it does not matter, because you must get the ideas very clear. So, for example, now yeah. So, the whole target is now to compute P I j k, that means k step transition probabilities we want to compute. And so, here again I will just start from x 3 equal to 1 and x not equal to 1. So, suppose now in 3 steps you want to transition from 1 to 1. Okay. So, this again I can break up like this, x now starting with 1, you are in 2 steps in 1 state 1, and then you will be going again transitioning to 1, right. So, this is your 2 step transition probabilities, and then this is your 1 step. So, again I can write down this, and now these 3 paths are mutually exclusive and exhaustive, right. There is no, because you can go to x 2, you can be at after 2 steps, after 2 transitions, you can be in state 1, 2 or 3, right, starting from x not equal to 1, and then you have to transition finally to state 1. So, therefore, these are the 3 paths, right. And here again we are using the Markov property, because this one is this, then this part of the path will be independent of the probability for this, because here you have x 2 equal to 2 and x 3 equal to 1. So, only the current state is needed to compute the transition probability, and this is not dependent on where you were earlier, either at x 1 or at x 0, that is not important. So, therefore, we will write this, and again using stationarity I will simply be able to write this also again as a 1 step transition probability of going from 3 to 1. Right. So, therefore, you see that these 3 probabilities can be written as P 1 1 2, yes, in 2 steps you are going from 1 to 1, and then again in 1 step you are going from 1 to 1. So, this is P 1 1 2 and P 1 1, right. Similarly, 2 step transition from 1 to 2, 1 to 2 P 2, and then 2 to 1 P 2 1, plus P 1 3 2 and P 3 1, right. This is here, right. So, and then I can write down x 3 equal to 2 when x naught is 1, and then of course, probability x 3 equal to 3, x naught equal to 1, right. This will also be equal to, so p 1 1 p 1 3 plus p 1 2 p 2 3 plus p 1 3 p 3 3. So, this is the first row of, and you can see that since this is your element of p square. So, therefore, if you write these are the entries of your p square, and then you are again multiplying by p 1 1, p 2 1, p 3 1. So, that means essentially, yeah, okay. So, we saw that P 3, that means if we want the 3 step transition probabilities, this will be given by P 2 P square into P. So, again a third power of P, and so in general we can now say that if we want n step transition probabilities, then this will simply be raising the matrix P to power n, that means multiplying P n times, and the entries in P n will give us all the n step transition probabilities that we need, right. Okay. Now, there is another method through walks on the transition graph, but you will soon realize that it is not a very efficient method. It is fine to see what is happening when your graph is small and the number of states are also not too many. So, for example, when you want to look at this probability of 2 step transition probability from going from 1 to 1, right. So, which would mean that you traverse this loop once and then again one more time. So, 2 times you traverse this loop and you have this, then you can compute the probability, which would mean that since the probability of traversing the loop once is p 1 1. So, when you do it twice, it will become, so the probability would be, so probability of this would be p 1 1 square, right. Fine. Then if you want to for example, compute the 3 step transition probability of going from 1 to 1, then let us see what are the, so we will try to see all possible paths on this transition graph of going from 1 to 1, right. So, of course, I have not written the details, for example, x naught equal to 1, x 1 equal to 1, x 2 equal to 1 and x 3 equal, I have just made the notation simpler. So, here this tells you the one path, which is you are traversing this loop 4 times, right. I mean 1 to 1, so 3 times, 1 to 1, then 2 and then 3 times, because 3 step transition probability. So, this path you will traverse 3 times, that means a loop you will traverse 3 times. Then the possibility is that you go from, you traverse the loop once, then you go to 2 and then from 2 you go to come back to 1, right. So, you traverse this loop twice, then you go to 2 and then 2 to 1. So, this is one path, and therefore, here again you can write down the probabilities as p 1 1 square into p 1 2 plus p 2 1, right. So, once you write down, so there are 8 possible paths, you can see that, right, 3 step transition, and you have in this 3 possible states. So, therefore, 8 possible paths, and similarly like 1 to 2. So, you go from 1 to 2, then you traverse this loop 2 to 2, then 2 to 1. So, this will be p 1 2 into p 2 2, then p 2 1, right. So, this way I can write down all the probabilities and then compute the. So, therefore, they are all distinct paths and you can compute the probability of each path, and as I told you, each leg of the path is independent. So, we are multiplying the corresponding probabilities of traversing each leg of the path, and so you can write down. But you see that this will become really cumbersome the moment your number of states become, if you had 4 to 5 states, or even easily any Markov process that you consider may have 7 to 8 or 10 states, then you see the possible number of paths will really go up, right, exponentially, and then you may since it is very likely that you will miss out on some of the paths, because you have to enumerate all possible paths, and here in this case only for x 3 equal to the 3 step transition probabilities for one going from 1 to 1, you had to enumerate 8 paths. Now, if it becomes x 4, it will be 16 paths, So, the number just will blow up, and so therefore, this is for large n and for large number of states. That means, if you want 10 step transition probabilities and your number of states is also 10, then it is just not possible for you to enumerate all possible paths and then compute the probabilities. But for small cases, and in fact, to see actually what is happening, this is a good way, right. So, I thought I will just talk to you about it, and when you are working out small problems, you can actually see this, but otherwise this is really a very efficient way of computing the higher order transition probabilities. Okay. Now, this is fine. So, therefore, we have now a method of computing any step transition probabilities, provided we are given the one step transition probabilities, right. But again there is some more information that we need, and that is see, the value of x naught is not known with certainty. We do not know in which state the system was initially, or from where it started, right. So, this will be normally given by a probability distribution. That means, you will be given these values. So, p I naught is the probability that x naught is in state I, right. So, this at time 0, that means, at initial time the employee is in state I. So, this is there is a probability attached to it. Now, if you want to compute the probability that the employee is in HR, in human resource section division, at time 5. So, that means, you want to compute yeah. So, let us see, we want to compute the probability that x 5 is equal to 2. So, the particular employee at time period 5 is in HR, right. Now, let us see the column of P 5, remember the 5 step transition probabilities are given by P 5. So, the column would be P 1 to 5, P 2 to 5 and P 3 to 5. So, actually I should have written this, let me write this instead of immediately jumping to this. So, we want to say that probability x 5 is equal to 2, given that x naught is 1, right. Then you will multiply this by probability x naught equal to 1, right. So, I am writing this as a conditional probability then into the, so then, and I will have to do it for all possible values of x naught. So, to get the probability that x 5 is equal to 2. So, this will be probability x 5 is equal to 2, given that x naught is 2. So, probability x naught is equal to 2, right, plus probability x 5 is equal to 2, given x naught is equal to 3 into probability x 3 equal to x naught equal to 3. So, I break up this. So, again you see, mostly what you have seen that the basic probability theory that we need for analyzing these stochastic processes. So, this is writing probability as a breaking it up into conditional events and then writing them down as the sum of these conditional probabilities, right. And so, this one gives you, this is your 5 step transition probability from 1 to 2. So, 1 to 2 5, and then into probability x naught is equal to 1, which is given to you from here. So, P 1 naught. So, this will be P 1 naught, right. Similarly, this will be 5 step transition probability of going from 2 to 2. So, this is P 2 to 5 into probability of being in state 2 at time 0. So, which is P 2 0, P 2 0, and this is the third one. So, this is how you can now write down the probability if you want to know that in time period 5 the employee will be in HR, right. And so, you can now compute in general, you can say that this is now P I n will be the probability that the system is in state I at time n. And see here, just to make the presentation simple, I am just taking all the time referring to our job assignment example, but you know that this can be made to whatever the number of states general, you can have a symbol k here. So, k states and everything can be argued with respect to general number of states, but here I am doing it for this particular example, just so that you can fix your ideas better. Okay. So, then PIN is probably xn equal to I, that means the system is in state I at time period n. So, these are the probabilities and I have shown you how we will compute them. So, okay, you can write them down right here. So, this will be your I am writing it as small p naught into p n. Yeah. So, when you want the probabilities of the system being in a particular state at time period n, then this is the formula, and these are called the state probabilities at time n. So, this is the important, right. So, now we do also have the, see, we have the transition probabilities for any time period, and we also have the state probabilities at for any time period n, right. And yes, so okay, I have written it here. So, that means I am saying that if P n is your row vector of probabilities, so this was the ith component. So, then P n is yeah, I should have written here, this is the ith component. Yeah. So, in general, so if this is a row vector is P 1 n, P 2 n, P 3 n. So, that means state probability of the system being in n being in 1 at time period n. This is probability of the system being in state 2 at time n. This is the probability of the system being in state 3 at time n. So, I denote this by a row vector P n, and then this can be written as P naught into P n. So, this gives the state probabilities at time n, right. Now, the Markov chain is completely specified when you are given the first step transition matrix P and the initial probabilities of the system being in a particular state. So, P naught is the vector which gives you P naught 1, P naught 2 and P naught 3. So, these will be the probabilities when the initially when the system is in state 1, 2 or 3, then you can compute these, and of course, you can compute the transition probability, n step transition probabilities also. So, let us consider an example, the same example now with numbers, and so we will just go through all the concepts that we have talked about, the transition probabilities and the state probabilities, I mean higher order transition probabilities and the state probabilities. So, suppose the transition matrix is given as this. So, then the corresponding diagrams you see, for example, there is no arc from 2 to 1. So, therefore, this is missing here, and similarly you do not have a loop from 3 to 3. So, it is missing, the probability is 0, right. Otherwise, and you see that they add up to 1, all these probabilities, the rows must add up to 1. So, this is a valid transition matrix, entries are either positive or zeros, and the row entries all add up to 1. So, this is a valid, and the accompanying diagram is this, the transition diagram is given by this, right. Now, let us compute second order transition probabilities. So, I multiply P with P and I get these numbers. So, for example, here you can transition from 1 to 1 in 2 steps. This will be 1 to 1. So, 2 steps, therefore, again the same thing as I showed you, that if you want to see it on the path, it will be 1 by 4 this, plus then you can go to okay, you can't go to 2 in one 2 step transition, because then you can't come back to 1, right. So, then it will be, you can go to 3 and then 3 to 1. So, this will be 3 by 4 into 1 by 4, right. See, you can either stay with 1 to 1 and then, or you can go from 1 to 3 and then 3 to 1. This is what you can do in 2 steps if you want to transition from 1 to 1. So, 2 possible paths, and so therefore, this is 3 by 16 and this is 4 by 16. So, 7 by 16, right. Similarly, you can maybe look at this one here, 5 by 16. So, this is from 1 to 2. 1 to 2 you want to transition in 2 steps. So, then the possible path is 1 to 2, then 2 to 1, right. So, that will be what 1 to 2 is 1 by 4 into, you transition from 2 to 2 will be 1 by 2 plus, or you can go stay from 1 to 1 and then go from 1 to 2. So, that will be 1 by 2 into 1 by 4, right. So, what, how much will this be? 1 by 8 plus 1, or what, have I missed something out? So, this is you are going from 1 to 2. 1 to 2 you are going in 2 steps, yeah. So, 1 by 2 Yeah, this is 5 by 16 and you are computing P12, right. So, you can go from P11 into P11. So, that was 1 by 4, and why did I multiply it by, I want to go from 1 to 1. Okay, sorry, this is not correct. Why should I say it 1 to, this is simply 1 to 1. So, this into P12. So, therefore, this is half, that is okay, I wrote this plus 1 by 2 into 1 by 4, or I can go from 1 to 2, which is 1 by 4, and then transition from 2 to 2. So, that comes out to be 2 by 8, and I am getting it as 5 by 16. So, let us multiply this, that means you want 1 and 2. So, that will be I am missing out on a path, 1 by 8 plus 1 by 8 plus 1 by 16. So, 1 by, if you want to go from 1 to 2. So, the right, I missed out on the path. So, this is 1 to 1 and then 1 to 2, then 1 to 2 and 2 to 2, and then there is another path 1 to 3 and 3 to 2. So, plus 1 to 3 is 1 by 4, and then from into 3 to 2 is 1 by 4. See, that is what I was trying to say, that even in such a small diagram I was missing out on a path. So, just imagine if you had 5 or 6 states, and then you had that many nodes. So, and then you had these so many arcs, you will certainly miss out. It will be very difficult, or it will be very time consuming to enumerate all possible paths. So, as it is such a small example, I could miss out on the path 1 to 3 and 3 to 2. So, that will give you now 1 by 8 plus 1 by 8 plus 1 by 16. So, that will be 5 by 16, right. 1 by 8 plus 1 by 8, which will be 1 by 4. So, that is 4 by 16 plus 1 by 16, 5 by 16. So, anyway, you can now interpret all these probabilities by looking at the path or by fine. Now, I made further computations, took powers of p. So, this is p3 comes out to be this, and if you make compute the fourth power, then these are the numbers. Okay. And another aspect that I want to point out here is that, for example, in this particular case you are able to transition from any state to any state, even though some of the arcs are missing, but even after that you can go from 1 to 2, 2 to 3, 3 to 1 again, and so on. So, you can transition from any state to any state, maybe not in one step always, but in fact, here it is happening that you are able to go, for example, from 2 to 1 you cannot go in one step, but you will be able to go from 2 to 3 and then 3 to 1. So, in 2 steps you will be able to transition. So, here in fact, the moment all your entries, see at P2, so at P2 all your entries are positive, which shows, see, therefore, that means your Pij2 is positive for all ij. So, this immediately makes you conclude that you have a two step path from each state to, from every state to every other state. Okay. So, that means so the word for this is communicate. That means all states communicate with each other, and maybe not in one step, but at least in 2. So, if all entries of Pij2 are positive, then that means all states communicate with each other. I will formally define that also, but essentially what I want to say here is that you can go from any state to another state in 2 steps in this particular example. And in some other example, if it is there is some k for which this is positive, then that means again there is a k step path from every state to another state. Okay. And so, now when you look at the fourth power of p, these are the numbers, and you can now if you carefully look at the column numbers, this is 103 upon 256, 102 upon 256 and 102 upon 256. So, the numbers are getting closer, right, and we can say that almost converging to 102 upon 256. In fact, you might say that why not 103 or 102, but anyway one of these numbers. So, in other words that if you want to interpret these numbers, that means now the probability, say for example, what is this number? So, 103 upon 256 is the probability of 1 1 4. That means 4 steps you are from 1 to 1, right, and then 102 upon 256 is the probability 2 1 4, right. That means if you, so here it says that if you are initially in state 1, then in 4 steps you will be back in state 1. So, this is the probability. Now, this says that if you are in state 2 in the beginning and you transition to 1 in 4 steps, then this is the probability, and the third one is 102 upon 256. So, this is P 314. So, that means you are in state 3 and you are transitioning to 1 in 4 steps. So, you see that it is becoming almost immaterial to know from where you started, because these probabilities are getting closer, and we will show you, then later on we will also formalize all this discussion. So, essentially the state in which you were at the initial time is becoming unimportant. These, and similarly the same thing you can interpret for the second column, because it is 85 by 256, 86 by 256 and 85. So, these numbers are also getting closer to 85, and here I have written, because here it is 68 by 256, 68 by 256 and 69 by 256. So, you might say that why not 68, but then see, remember the probabilities which, when you finally say that all these are converging to, they must also add up to 1, right, because the system has to be in one of the states. So, the same argument we will continue using, and so here if I say that this converges to 102, this to upon 256, this is 85 by 256, then this should be 69 by 256. Of course, it is possible that they, so essentially right now the probability of being in state 1 after 4 transitions is hovering between 102 256. So, which is a more exact statement. This is a more exact statement, right. Similarly, here also I can say the probability of being in state 2 after 4 transitions is between is in the interval 85 upon 256 and 86 upon 256, right, which is a very small interval, right. So, difference of 1 upon 256, and similarly here it will be 68 upon 256 and 69 upon 256. So, this probabilities, and if you take the fifth power, then certainly you will see that the numbers are converging, and we will talk about this formally in a way. Yeah, and also while we were talking of this, see, I wanted to point out that here again these probabilities, because it is now a row vector, this is a row vector, remember 1 by 3 we are writing. So, this is 1 by 3 and this is 3 by 3. So, then again this is 1 by 3. So, the 3 entries must again add up to 1, because at n after n transitions your system will be either in 1, 2 or 3. So, therefore, these probabilities also must add up to 1, right, which you can see here also that. So, anyway, these also add up to 1, and then now suppose for this job assignment problem, if your initial probabilities are given by 1 by 4, 1 by 4, 1 by 2, that means probability of being in production is 1 by 4, probability of being in HR is 1 by 4, and probability of being in sales is half, then you want to ask the question that what are the probabilities of being in state in 1, 2 or 3 after 2 transitions. So, that will be given by this, right. So, 1 by 4, 1 by 4, 1 by 2 multiplied by p square, and so these are the probabilities of being in so this gives you the probability of being in production after 2 transitions, right, and this is the probability of being. So, these are the state probabilities after 2 steps, after 2 time period. So, this is 21 by 64 and 18 by 64, and these probabilities also must add up to 1, right. So, now we are trying to give you some more characteristics of the Markov process, and we will do a lot of analysis in terms of these transition probabilities and the state probabilities. So, let us just want to show you the limiting behavior of these steady state probabilities. So, let us just graph the values of P13, P23 and P33 for different values of n. So, you see the starting vector is 1 by 4, 1 by 2 and 0. So, P13 for example 1 by 4 is 0.25. So, I am just starting. So, these are the time periods and these are your probabilities. So, numbers from 0.1 to 0.5. So, 0.25, see at time 1 it is in period 1 it is 0.25, then here also 4 by 16 is 0.25. So, in period 2 also this is the same, then it very slightly goes up in period 3 to 17 by 64. So, I am just showing it like this, and then it comes down to 68 upon 256. Now, 68 upon 256 is 0.26. So, therefore, it comes down to this is my value for 0.26. Okay. So, this is the graph for P13, okay, as it goes to different periods. So, the values transition probabilities. Then if you look at P23 now, P23 starts from half, right, then it immediately comes down to 0.25 because this is 1 by 4. So, 0.25. So, this is where it is, and then in the next one it goes to 18 by 64. So, actually my graph for P13 is this one, because very slightly it goes up and then again it settles to here. This is the graph for P23. So, P23 the P23 graph is this. So, this is from 0.5 to 0.25, then it goes up to 18 by 64. So, this is above more than 17 by 64 this, and then it again comes to 68 by 256. So, the same value as for P13. Okay, P134 and P234 are the same. Okay. So, this is how it is, and for the P33, see it is 0 in the beginning and in stage time period 1, then it jumps to 5 by 16, which is a little more than 1 by 4. So, little more than 0.25, and then it comes to 16 by 64, which is exactly 0.25, right. So, I have tried to just parallel it with this one here, and then it will be 69.256. So, the line is slightly above this. So, therefore, you can see that, and then as you take higher powers, all three will settle down to this number, which we have to compute, and we will do it when we find out the steady state probabilities. So, you see this is the limiting behavior, and so it does not matter even though the three had very different starts, all the three, but finally they merge to the same. So, therefore, the relevance of the starting state of the process is not at all relevant here. This is what we want to show, and of course, this will this will not always be true, and we will now then find out during the course of next few lectures as to when this is valid, or when this kind of limiting behavior is valid. Okay. So, what we are going to say is that rows of P n become identical to pi 1, pi 2, pi 3. Okay, all the rows, because it does not matter the starting state of the starting state of the system, and so all the rows will be pi 1, pi 2, pi 3, but it is not necessary that the three probabilities are the same, right. So, that means it is so essentially what we are saying, this is now a long term behavior. We are saying that the system will be in state 1. So, that is the probability, right. Then this is the probability of the system being in state 2. And this is the probability of the system being in state 3. So, the starting probabilities are not relevant, but the values the long run values will not necessarily be the same. Okay. And so, the definition for the steady state probability is that pi j is the limit of p j n as n goes to infinity, right. Remember, we define this as the multiply by p 0 and p n. So, this is limiting value of p j n, n goes to infinity, which is actually probability x n is in j, right. In the long run, your system is occupying state j as n goes to infinity. And what we are saying now is that this actually is equal to this conditional probability, but this part is becoming irrelevant, right. So, the I see the probability finally is going to pi j. So, the I part is irrelevant here. This is what we want to show you, and so we will in the next lecture discuss the under what conditions. Well, of course, that will come in the due course of time, but first of all we would want to know how we go about computing these steady state probabilities when we know that they exist. So, right now we will assume that they exist, and then we will find out the method of computing them, and then we will continue with the discussion as to under what conditions they always exist.